pencils. Yeah, when I was younger.
Oh, wow. When I was younger.
Like 2 years ago. What are you talking? I don't know if I can even start running anymore. My back's so bad.
How's it going?
Good.
Good? Everybody remember we do not have class Friday? Yes?
Oh, yeah.
Okay. Yeah. That was a hard one to forget, right? This is homework for next Wednesday.
Oh, Dr. Joe!
Oh my God.
What? Whoa. What is going on?
Because I never give you homework.
Is this what we're working on class today?
Yes.
We're working on homework.
No, we're working on problems like these in class.
We're doing these specific 6 problems, right? No. What are these 6 problems?
Homework for Wednesday.
Problems?
I'm not here Friday.
Oh, we have a class Friday.
Hey, Michael, also be here class, okay?
Also, I posted an extra video on YouTube that does 5 problems from the same packet. Oh, they're not the same problems.
That would be fun.
I was already on YouTube.
Dr. Joe, we talked about maybe taking this down to like 5 problems.
I can talk about moving it up to 10.
Let's relax on that one, Chief. Let's relax. I need extra practice.
Actually, I can tell you which problems are the ones that are on the video. The video has problems 21-2, 21-8, 21-10, 21-12, and 21-20. So 2, 8, 10, 12, and 20 are on the video.
Do we know how to do all these by the end of the day?
Yes.
Okay, well, now I have to contemplate it.
Do what we do with it. I still want you to have an opportunity to ask me questions. I'm leaving tomorrow. I'll be here Friday. I still think you have an opportunity to ask me questions. All right. All right, so let's talk more about Flyzone distribution, and let's just do some example problems today. Because last time was more of a derivation day, which I didn't get I didn't get any opportunity to show you problems. So remember again that the idea behind Flyzone distribution is that you've got items, whatever those items have to be, that are arriving at over a certain time period, and you know the average number of arrivals per time period. Right? That's what the lambda was. So with your parameter then, that lambda is the average number of occurrences, arrivals, however you want to think of it. It's per whatever the time period is. Now, in some of the problems, you'll be given the average amount, the average number of occurrences per one time period, but ask you to compute probabilities per a second time period. Hi, Sam. You came in huffing. So what I mean is, you might be told that the number of customers arriving in a bank each hour averages 5 per hour, but ask you the probability that you see 6 in a 2-hour period. You just have to read them carefully because it's not a hard thing to convert from one to the other. If the average is 5 per hour, how many would you expect to see in 2 hours? 10. So that would be your new lambda. That's the problem. So that's not a hard thing. It's just you have to read the problems carefully and make sure that you've got the right time period for what you're doing the probabilities for. Okay. So not a hard thing to switch. It's just you have to pay attention to it. That's why I'm mentioning it. Right. So remember our PMF for a Flyzone variable is that e to the minus lambda, lambda to the x over x factorial, where your x's are the whole numbers. So x goes 0, 1, 2, 3, and so on. Drop that down. Sorry, Clarence. I know. I'm a jerk. It's fine. Well, the Poisson is French. I'm trying to remember what the derivation is. I can't remember. It probably was from, well, the Bernoullis were French for certain, so it wouldn't surprise me that it was French. I can't remember why. Yeah.
How'd you say it?
L'Hôpital. L'Hôpital. El Hospital. Happy Towel. The Happy Towel rule. It's kind of funny.
Next time we do that, tag this up.
Happy Towel. I don't remember this. There is a story of why it's called Poisson, but I can't remember what it is off the top of my head. Ask Dr. Roth, he can tell you, I'm sure.
That's Dr. Roth.
He talks about probability in math history. So, all right. Anyway, we also talked about the moment generating function. So your moment generating function was e to the lambda times e to the t minus 1. We did derive that last time. The reason why we derived it was so that we could figure out what the mean and the variance are. And this is why it's Haley's favorite distribution. She just told us that last hour. What are the mean and the variance for the Poisson distribution? Lambda, yeah. So, again, like I mentioned, for your next test, which is what, the 15th? You can come in earlier in the day, too. So, anyway, this would be the type of thing that you'll have to fill in the blank part on your first page. Same kind of thing. So, you need to know this for the discrete distributions that we've talked about. Okay? All right. So let's see if we can do some problems that actually involve using this stuff. So to start this from the sheet, I gave you sheets last time over the 21 stuff. Okay. Didn't get to it, but I gave it to you last time. Let's look at 21.1. All right, so they tell you that x is has a Poisson distribution. The lambda is 1. It says, what's the probability that x is greater than or equal to 2, given that x is less than or equal to 4? So start off with a conditional one, since I know you all like the conditional probability problems. It's great, isn't it? All right, so using your conditional probability formula, how would we calculate this? Just with the conditional probability formula, not with using the distribution yet. Just with conditional probability, what would we write? Okay, probability that we have x is greater than or equal to 2 and less than or equal to 4. Oops, it's an x. Maybe it's an x. X over. Good. So I think the first thing I would do before I even start trying to put things in the distribution is see how I could rewrite the top to help me out a little bit. I want x is greater than or equal to 2 and less than or equal to 4. What does that mean about x? 4 or 4, right? It's between 2 and 4. Do we agree? And now it's just a matter of using the distribution. Because this one means 2 or 3 or 4. This one means 0 or 1 or 2 or 3 or 4, right? So we just need to plug in the values into the distribution to get those. So on top, lambda was what in this problem? 1. So we would have e to the negative 1. That's going to appear in each of them, right? Right? So I'm just going to pull it out. E to the negative 1. The first one, if we look at back, let me scroll back up to the formula here, maybe. Here's our formula, right? Yeah. So I'm just all of them are going to have an e to the negative 1 in it, so I just factored it out in front. Lambda is 1, so the numerator is always going to be 1 for the rest of the terms, right? So on top, we'll just have 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial. And again, the reason why these are 1s is because the lambda is 1. Technically, it's 1 squared, 1 cubed, and 1 to the 4th, right? Because it's lambda to the x. What does the denominator look like? Well, it comes out in front. The e to the negative 1 again, right? Because it's going to be in every one of the terms. And then what do you have to add together? 1 over 0 factorial. Yep, that's right. That's literally just plugging and chugging it with the formula, right? Not anything fancy. Unlike the rainbow colors that I'm using, those are very fancy. It's different than the other one. Haley liked this one better last class, so I stuck with it. I can see it doesn't have that light green, so it's a little bit easier to see. But it's still festive. Which is the most important thing, right? It is math. Yeah. What'd you say, Megan? Oh, good. All right, so notice that your e to the negative 1s will cancel. Yes, Michael? Yeah, the e's to the negative 1s will cancel, so we just need to go through and calculate. Oh, goodness. A half, a sixth, and the 24th, so 1 24th, 4 24ths, 4 24ths, so you have, what, 17 24ths on top? Is that right? And then on bottom, let's see, we've got 48 and 17, so 65 24ths on bottom. Hey, look at that. There's an answer, so I'm going to pretend like I did my arithmetic right. Yes. 0 factorial is going to be 1. Yeah, 0 by definition, 0 factorial is 1. It's 1 plus 1. Yeah. It is 2 today. Could be a different number tomorrow. Let's hope. Has to get in the odds. Could be 0. 0 factorial is okay. Is it okay? Yes.
Do you know if you vote on the laws of physics that if the majority wins, that's what it counts?
Oh, really?
Yeah.
Okay. That's bizarre.
It's like you vote on gravity works or not.
Let's do 21.3. Democratic physics.
Hey.
Don't be bored on your head.
Yes, please, dear God.
Yeah.
We're all gonna blame you saying that.
Yeah, usually they do. Yeah, usually they usually blatantly say it's Poisson. Yeah. What happened?
I don't like leave in time out because I don't know what he's talking about.
Oh God.
I don't think he actually listens to it.
I don't think he actually listens to us.
Well, there is that. All right, 21.3. This is what I was talking about at the beginning where you have to pay attention to the time periods. Notice I tell you there's an average of 1 transmission error per 10 seconds But what are we asked for the time in the time period for the probability?
30.
Yeah, a half minute, a 30-second transmission, right?
So there's 3.
So what's your lambda going to be in this case? 3. Okay, so again, the reason why it's 3 is because there's an average of 1 error each 10-second period. Oops. And there are 3 10-second periods. Okay. By the way, this is where the independence part of the occurrences come in. That's what's allowing us to just basically multiply this by 3. So it's independent. The average in the first 10 seconds has no effect on the next 10 seconds. So that average has to be 1 as well, which has no effect on the next 10 seconds, and that average has to be 1 as well. So that's why the average over the whole 30 seconds has to be 3. That's where the independence part's coming in. That's what's allowing us to have that together. This independence idea and doing addition of these distributions is going to pop up later when we start talking about doing what are called multivariate distributions and doing things like adding distributions together. So it's one of the reasons why I'm mentioning why we're allowed to do this now. All right, so we want the probability of more than 1 error. With the probability of more than 1 error, so we want the probability that x is greater than 1, which for a Poisson distribution, which means it could be 2, or it could be 3, or it could be 4, or 5, and so on. You have to calculate an infinite sum, right? Well, it's probably easier than actually calculating that infinite sum. Yeah, do the complement, right? What is the complement of more than 1? Yeah, less than or equal to 1, right? So we can do the probability for 0 and the probability for 1. Probability for 0 will just be e to the minus 3, because you'll get, doesn't matter what lambda is, lambda to the 0 will be 1 and 0 factorial will be 1, right? So it's just e to the minus lambda for 0. And then for 1, you would have the e to the minus 3 times the lambda, so you would get 3e to the minus 3. It'd be over 1 factorial. You'll get used to these, writing it for 0 and for 1 quickly. You'll do enough of them where you'll have to do 0s and 1s quickly. If you need to write out the formula, fine, write out the formula. I'm just saying that when you do the 0, all you're going to do is get e to the minus lambda, because the other pieces are 1. When you do for 1, you'll just have lambda e to the lambda, because it's lambda to the first over the 1 factorial. So you just get a lambda. So you get, what, 1 minus 4e to the third? Or e to the minus third, sorry. Which? Okay. Or answer C, it looks like. That one okay? Let's do another one. Why not? Let's do another one. Marking here. Let's do 2114. It's a little bit different. It's a little bit more complicated. 2114. One of the reasons why this one's a little bit more complicated is that there's a hidden conditional in the problem. So, if there weren't this hidden conditional in the problem, this problem wouldn't be all that difficult. If you were just looking for the expected number of claims in a year, 10% of the time, the expected number of claims is 0.6, and the other 90% of the time, the expected number of claims is 0.1, how would you figure out the expected number of claims if it was just that? If 10% of the time it was expected to be 0.6 and 90% of the time it was expected to be 0.1, what would you do? You would just multiply, right? You take the 0.1 times the 0.6 and add 0.9 times the 0.1, right? If 10% of the time you expected 0.6 of it, you would take 10% of 0.6, and 90% of the time you expected 0.1, you would take 90% of 0.1, and then add the two together. Unfortunately, that's not the answer to this problem. Even though 0.15 is an answer, that's not the right answer to this problem. I've told you now that there's a hidden conditional in here. So where's the hidden conditional? It says that, notice at the end, it says calculate the expected number of claims made in a calendar year in 1998 by a customer who made one claim in 1997. So here's why there's a hidden conditional. You're trying to figure out basically the probability of being a high-risk customer or not, given that there was a claim made in 1997. Because what did I do when I said if I didn't have that hidden conditional, what did I say we did? There's a 10% chance you pick a high-risk customer. There's a 90% chance you pick a low-risk customer, right? So you would take the 0.1 times the 0.6, the 0.9 times the 0.1, right? But you're given more information than that. You don't know whether or not you have a high-risk customer, but you're given a little bit more information. You do know the customer made a claim in 1997, right? So we need to figure out what's the probability of being a high-risk customer given you made exactly one claim. And the reason why we need to know this is we're trying to figure out what is the percentage chance of this person that we're calculating in the probability for in 1998 is a high risk, right? Because a high risk person has a higher incidence of claims than a low risk customer, right? Think about why an insurance company might want to do this, by the way. You've got somebody who had an accident the previous year, but they're trying to switch insurance companies, right? So the new insurance company wouldn't know whether or not this person would be considered a high-risk person because they don't have that information from the previous insurance company. The previous insurance company is not going to give up whether or not they think it's a high-risk customer because that would be proprietary information about how they set their premiums, right? Allstate's not going to tell State Farm how they set their premiums and how they classify their customers. It's not going to happen, right? They're just going to have competing funny commercials, okay? Right? But they're not going to tell one or the other how they classify their customers. But maybe an Allstate customer made a claim back in the previous year and now wants to switch over to State Farm. State Farm wants to know, okay, well, I can check to see whether or not they had a claim because that has to be disclosed. How bad of a risk is this person really if they had a claim, right? Be able to set what the premium should be. So that's why an insurance company might want to know this. What's the probability that they're a really bad customer? I need to charge them high premiums. Or they just got unlucky the previous year. And then factor that into the premium calculation. That's why an insurance company might want to know this information. So we're going to do that for our purposes using this conditional then. So using our conditional formula then, we want the probability of high risk and exactly one claim over probability of high risk, or no, sorry, probability of exactly one claim. Did that backwards. So the top of course, is you'll do probability of high risk, probability of exactly one claim. Oops. Given high risk over probability of exactly one claim. This is a Bayesian problem, right? Right? This is a Bayes theorem type of problem, yes. We've done ones like this. All right, so top, probability of being high risk. What is the probability of being high risk? 10% or 0.1, right? Given that it's a high risk customer, how are we going to calculate the probability that that customer made exactly one claim? What distribution are we using? The Flyzone, right? What are we using for the lambda if it's a high risk customer? 0.6, right? Because they tell us the mean is 0.6, right? So exactly one claim then would be 0.6 e to the minus 0.6. Like I mentioned a minute ago, if you plug in 1 for x, you're going to get lambda e to the minus lambda, right? Think about what your distribution looks like. If I put in 1 for x, this is 1 and this is lambda. Right? So that's our numerator. Everybody okay with the numerator? Okay, let's look at denominator. Exactly one claim overall. Well, how can you make one claim? There's a couple of ways, right? You can make one claim and you are high risk, or you can make one claim and you are low risk, right? So we have already done high risk and one claim. How do we get low risk in one claim? 0.9. Fantastic, good. So the 0.9 comes from the fact that that's the probability of being low risk. And then again, we're just using the fact that we have exactly one claim, so it's lambda e to the minus lambda. So this looks like a good calculator problem. Grace, Grace, Grace. Michael's just staring at her. He makes everybody nervous. 0.2879. Yeah.
No. It's not an answer. It doesn't make sense.
Well, it doesn't matter. It's an answer. That's what's just part of the answer. We're not done with the problem.
Oh, okay.
It's like that number may.
Everybody was being mean to me for a second.
Pretty close to 0.3. That's not this. Also, not necessarily the answer. All right. Why did we calculate this? Besides the point that I told you to. Why did we calculate this? Remember how I started this problem? I said if we didn't have the given information, we would take the percentage of high risk and multiply it by the mean for high risk, and add to the percentage of low risk times the mean for low risk, right? But that would be saying that if I just randomly select a person, there's a 10% chance that person's high risk, 90% chance that it's low risk. But that's not what we have here, right? We're given additional information. What's the probability this person that we're talking about is high risk now?
0.2879.
Yeah, that probability, right? Okay, so what do we want to multiply that probability by then? Okay, so the expected number of claims then. Okay, we take the 0.6 times the 0.2879. Right? But we're not done with this. About 29% of the time, that person's a high-risk person. Right? What else do we need to do then? 0.1 times the rest of the time, right? Either they're high risk or they're low risk, right? Right? Those are the two choices. They're either high or low. And what do you get?
This to be Michael. 243.
Whatever. It's only 2 decimal places on here anyway.
C.
So it's C.
Yay.
Questions on that one? You okay with that one?
No,
I guess so.
I didn't call you anything.
What?
What did I call you?
Oh, Michael.
Oh, why don't you hit Michael then?
That is a solve.
Who said that?
I feel like she's acting self-defense.
Sounds like self-defense to me.
So,
All right, let's look at 21.19.
I would testify that.
you don't lie.
I would be lying.
I didn't know.
Because you think it's not self-defense, I don't think it's self-defense.
But in the court of law, there is a definition of self-defense as well as self-defense.
Oh my goodness. 21.19. Work on it for a minute and then tell me how to do it.
Well.
Boo. Did you say boo? Is what one? Well, the lambda to the x over x factorial will be 1, but the e to the negative lambda won't be. It's still e to the negative lambda. You're not putting an x in that.
Oh,
Show me what you did.
Right?
Oh, wait, so the race function is out there.
all right, I will slave away for you.
Thanks, Grace.
Yeah.
Well, I might have done it wrong. So I don't want to say my answer would be wrong. Can you come check what Who's gonna answer? Did it do it right?
Everybody was asking, look at the answer, and I had that answer.
Okay.
And if we're going to vote, then I'm going to say that's the right answer.
I don't know how we trust that.
There has to be something really, really subtle, as short as that problem is. We're ready to talk about it? All right. I think the only real quote unquote subtle part is doing what? Make sure you make the right lambda, right? Because the mean per week is 2, and they ask you for probability in a 3-week period. So what's your lambda? 6. And then it says fewer than 4. So strictly less than 4, right? So you have to do 1 or 2 or 0 or 1 or 2 or 3. So 0 or 1 or 2 or 3. This one should be 6 squared over 2. This should be 6 cubed over 6. Yeah. And what did you get, Grace?
0.1542. Yeah.
Yeah. That one okay? Yeah, Sam.
So if we would have done it, would it be possible to do a blend?
I don't think so. You could do it with lambda equal to 2, but then you would have to do the different ways that you could possibly get 3 or fewer in 3 weeks. So if you did the probability that you had, you could do 0 in the first week, 0 in the second week, 3 in the third week, or 1, 1, 1, and you got all those different. You could do it that way, but you'd have all those different combinations that you'd have to calculate. You would have to do, but it's fewer than, so you'd have to do 0 or 1 or 2 or 3 with the different choosings. So it would be a lot more, you could get there, but it'd be a lot more cases to have to try to handle. Okay, try 21.13 now.
All these tornadoes.
Well, a lot of these problems are for actuarial exam review. Actuaries set problems for insurance. Insurance companies are worried about tornadoes. It was like the Kevin Bacon game. You know, you start with an actor and see who they start with. You get your Kevin Bacon. I've heard of this. 6 degrees separation of Kevin Bacon. So start with an actor and then figure out a movie that actor was in with somebody else and work your way back to the movie that was in with Kevin Bacon.
I feel like you talked about it.
I probably talked about it before. Yeah. Oh, yeah, there you go. There's actually what's called a collaboration distance number for mathematicians, which is about, you know, if you co-authored directly with someone, your collaboration distance is 1. Or if you co-authored with somebody else and co-authored with somebody else, that collaboration distance is 2. I've heard of that. Anyway, that's not nearly as interesting. More fun. It is. They actually have a website where you can type in your name and another mathematician's name. Almost everybody goes through called heritage. No, it's not.
No, every big get posted like that.
he was absolutely ridiculous. Yeah. I've done a similar thing with trying to get through what are the mathematical genealogy. So like your academic fathers, your PhD advisor, and then going back that way to try to go through different lineages to get to different mathematicians that way too. Also not nearly as interesting, but.
Laplace. I don't think Laplace is in mine. Gauss is in mine. Gauss is in one of people's. Probably. Gauss. Fires for us. Gauss is a pretty big name.
No, it's telling you about the probability in this case. So you don't know what the lambda is for each of them. So you've got two different lambdas that you're working with. But you do know that how to calculate the probability given the lambda, you know how to do the probability. So that's what that was talking about. So I was trying to give you equations to solve, figure out what the lambdas are. That's okay. So just in general, it doesn't matter what the Gaussian variable is. What's the probability that someone can accept? Using your formula. So look at the formula. That's what an x is equal to 0, what I'm figuring out. Yeah. So that's telling you how to get an equation set up. That's what that's doing. Bye, Haley. You what?
I left something in the
Oh, gotcha.
Come on, guys.
I'm gonna ball game, though. That's right. Okay, way farther with what? The problem?
Like, I didn't think I would get this far. I'm not going to finish it.
It's my fourth class in a row today. Yeah. Teaching for Dr. Stuckey again, so. I hope. If not, I'll be doing it again on Monday. Well, yeah, because Dr. Miller's still not back. So in this problem, you've got two different Poisson random variables, right? Which means you're going to have two different lambdas. If you're going to try to figure out what the lambdas are, you probably need two equations. So the second and the third sentences hopefully are giving you ways to figure out the two equations, right? The second equation says the probability there are no tornadoes in region B is 1.8 times the probability there's no tornadoes in region A. Now, if my region B lambda is, say, lambda 2, how do I calculate the probability of no tornadoes in region B? Right, yeah, so it'd be, P of x equals 0 for region B. If x is 0, what do I get out for the probability? E to the negative lambda, right? So I'm going to call it lambda 2. So I have e to the negative lambda 2. What does that have to equal? We'll call it, yeah, good. We'll call it lambda 1. We agree? For the second part, it says 1 tornado. Well, what will the probability look like for 1 tornado here? So e to the negative lambda 2 times lambda 2, right? Has to equal 1.3. Okay? Times lambda 1. Oops. Okay. Okay. I agree. So what is it that we're trying to find? Well, just in general for the problem, what is it we're trying to find? In both regions, right? So we want, what is it? A over B, right? So we want lambda 1 squared e to the minus lambda 1 over lambda 2 squared e to the minus lambda 2. Oh, it is B over A. Thank you. And I know there should be 2's in those. Why didn't I put the 2 in there? Over when we do the probability when x is equal to 2, there should be a 2 in the denominator. Yeah, they're both over 2, so it'll cancel, right? So this would be your L over K, right? All right, do I really need, just looking at this, do I really need to know what lambda 1 and lambda 2 are? The answer to that question is no, I don't really need to know that information. What do I need to know instead? I need to know ratios, right? Can I get if I ignore the first part, can I get that ratio? What is that ratio equal to? It's 1.8, isn't it? This part right here is 1.8, isn't it? Right? If I know this ratio, can I get this ratio? Yeah, right? If we look at the second equation here, I know that lambda 2 over lambda 1 will be 1.3 e to the minus lambda 1 over e to the minus lambda 2. We agree? So this will be 1.3 over 1.8, because I know that e to the minus lambda 2 over e to the minus lambda 1 is 1.8. So this will be 1.3 over 1.8 squared times 1.8. Notice I didn't need to find lambda 1 and lambda 2 individually. In fact, I think it's impossible to solve for lambda 1 and lambda 2 individually.
Yeah. Two equations.
Right, but when you do the other equation, you're going to get a lambda times e to the minus lambda. It's not going to be, it'll be impossible to separate them is the issue.
Can you walk me down one more time, like why you have
how do you know that lambda 2 over lambda 1 is 1.3?
This part? I just moved this to the other side. I divided both sides by lambda 1 and divided both sides by e to the minus lambda 2. That's how I got here. I divided both sides by lambda 1 and divided both sides by e to the minus lambda 2.
Oh, I didn't see that.
Because e to the minus lambda 2 over e to the minus lambda 1 is 1.8. This is the reciprocal.
Wow.
And so how do you know that e to the lambda 2 is 1? Wait, what?
E to the minus lambda 2 over e to the minus lambda 1 is 1.8. This is the reciprocal. So that's why it's over 1.8.
I'm like kind of following you, but not really.
So whatever your 1.3 squared over 1.8 is your answer.
169 divided by 1.
What is it?
169 over 1.
Oh, yeah. Less than 1. All right, that's how you attack that one. Remember, we don't have class Friday because I'll be out of town. There's videos posted for the Flyzone, some of the Flyzone examples. One more thing before you go. There's a problem in your homework if you get to it. It's talking about the modes of the distribution. Mode just means it's the highest probability. So if it says modes plural, it wants you to set two things equal to each other. Equal to each other. Because if it's more than one mode, they have to be equal to each other. And mode just means it's the probability is the highest. So if you had probability is 0.2, 0.5, 0.3, 0.5. It's just whatever the biggest probability that value corresponds to that. In the problem, then you have to do, it's not important that it's the mode. The important part is that you have to set the two probabilities. Because it says it has modes at 2 and 3, so there's 2 modes. If it says modes plural.
Where?
Yeah.
Okay, thanks.
Yep.
Yeah, see this thing like that. Look.
Chelsea,
In my regular inbox.
when are you getting over there?
That's hilarious. That's awesome. Build a wall around your retirement. Wonder who they're going after. Oh, shoot. That's funny.
For those questions.
Yep.
Did they get the screen up?
It's working. Yeah, I just used it. Yep.
Okay, great.